Welcome everyone, thank you for coming. My name is Max LaFortune, and today I'll be presenting my part of the Alkaline Surfactant Polymer Flood Design Team project, which is the polymer aging tank. So to start off with, the purpose of the polymer aging tank is to adequately hydrate the solid polymer using the deoxygenated soft water, which comes from the polymer volumetric feeder. A hydrofoil impeller was chosen to ensure proper agitation and hydration, as well as to minimize shear rates so that the polymer doesn't break up. The product is then sent to the post-polymer filter, which is used as a precautionary measure in case any solid polymer pieces or fish eyes remain in the product stream, which would then be filtered out. The polymer aging tank operates at ambient pressure and temperature, which makes it ideal for energy efficiency. So, for the polymer aging tank, there are a few alternatives considered. First of all, I considered a mixing tee versus a continuous mixing tank, as well as batch mixers or a continuous inline mixer. The mixing tee was discounted because it was seen as not able to achieve the adequate hydration and uniform viscosity necessary, whereas batch mixers, although a viable option, would require multiple mixing tanks, and thus the capital cost would likely be increased. Finally, a continuous inline mixer would require a very, very long length, as well as a very highly turbulent level of fluid in order to achieve the adequate hydration. So those were limiting factors for that choice. As a result, the continuous mixing tank was chosen, which eliminates the need for multiple mixers and allows proper hydration and agitation to be achieved while minimizing shear rates using the appropriate impeller. Some of the practical issues and challenges that needed to be addressed. First of all, making sure that the appropriate viscosity was achieved, as well as a uniform viscosity, was very important. Also, avoiding polymer fish eyes as much as possible in the product stream was a key consideration. In addition to that, minimizing energy use, as well as ensuring adequate mixing took place, were also key considerations. Some of the design considerations were what the polymer and mass flow rate into the tank should be to ensure the proper viscosity, as well as the dissolution time required for the just suspended condition, which was required for this mixing to take place. So, some of the key equations and considerations were the Zwittering correlation, which was used to solve for the impeller speed, as well as the shaft power, which could be checked to ensure that heat was not building up in the tank, which would create dangerous conditions. So, for this tank, as well as its wetted parts and pipes, 316 stainless steel was chosen as the material of construction. It was chosen as it's actually an industry standard for strength and durability. And though the deoxygenated water will be coming in, it's also very corrosion resistant, so it will last longer. Using a correlation from Peter's design handbook, the cost was estimated to be at $48,000. As you can see from the piping and instrumentation diagram, safety was a key consideration in the design of this tank. Here we have a level controller, which is transmitted, a digital signal is transmitted from the level transmitter once the liquid height in the tank reaches 2.9 meters. This then allows the outlet flow to flow out of the tank and ensures that the 2.9 meters is maintained as the constant height in the tank. Because safety is such a key consideration in this tank, however, due to its high volume of water and polymer mixture, there were a few additional safety measures put in place. A critical alarm in case the liquid height reaches above 2.9 meters was put in, as well as a release valve, so that if all else fails and the tank liquid level reaches the top of the tank, the components will be allowed to flow out of the tank and thus not build up pressure inside. So, as you can see, this is an innovative design for this tank that will maintain safety and proper hydration of the polymer.